Welcome everyone to our YouTube series, Test Prep Made Easy. So in this particular series, we are going to post regularly questions on our YouTube channel. The questions may pertain to CAT preparation, maybe pertaining to GMAT preparation, as well as of various topics which are tested in these particular exams. For example, quants, LRDI, English, and various areas which are tested. And each day we will handle certain number of questions and their video solutions. The best approach is to these questions in these videos. So have a happy preparation ahead and enjoy the video. Thank you.
All right, so these are the questions that we are going to try in today's video. If you have tried it already from the thumbnail, good enough. If you haven't, you can pause the video at this point and try it once before you look into the solutions. We recommend you doing that. But if you just want to enjoy the solution, that's also good enough. And go ahead and watch the solutions now. All right, so we have a question in which it says there are three numbers, couple of them are given, and the third one is missing. The LCM of these three numbers is this. Great. So it's a pretty easy question because I find something about these two numbers and the LCM value, which makes this a very, very easy problem. But let me explain this with a very basic thing. So whenever you need to find the LCM of any set of numbers, so let me just take a random three numbers or something, and I hope everybody is aware of it. If you are aware, just bear with me. So I'm explaining so that everybody understands what I'm going to do with this particular question. Suppose you have 2 to the power 4 into 3 to the power 5 as one of the numbers. You have 2 to the power 5 into 5 to the power 6 as another number, and you have 2 to the power 6 into 3 to the power 4 into 7 cube as the third number. So suppose we have these three numbers. It's very easy to figure out LCM if you have the factorized form. So in this case, I have this prime factorized form already, and it's pretty easy to find the LCM. So you need to understand that LCM is the lowest common multiple, right? So in turn, if you think for each prime number, so for example, for 2, it has to be whatever is the LCM, it has to be a multiple of 2 to the power 4, it has to be a multiple of 2 to the power 5, and it has to be a multiple of 2 to the power 6. So in turn, we can say that it needs to have a 2 to the power 6 in it. So basically the highest power of all of these primes. But I hope you understood the basic idea. Similarly, you can check this for the next prime, that is 3. So we have 3 to the power 5 and 3 to the power 4 in it. Okay, let me just take this thing off and write this again. So 3 to the power 5 and 3 to the power 4. So effectively, it has to be a multiple of 3 to the power 5 in order to be multiple of both of them. So it needs to have 3 to the power 5 in it. 5 just we have 5 to the power 6, and 7 just we have 7 cube. So effectively, this will be the LCM. So if you want to visually understand this, you just take the highest prime of each, highest power of each of the prime numbers, and that will give you the LCM. Similarly, if you need to ever find the HCF, say for these three numbers, what you need to do is you need to find the lowest power. So it's the highest common factor. So basically, it has to be a common factor and the highest among them. So obviously, anything 2 cube or 2 square will be a factor of each one of these three. But then the highest among them will be 2 to the power 4. Now here we can see that this has 3 to the power 5, this has 3 to the power 4, but this second number doesn't have a power of 3. So you can imagine this has 3 to the power 0. So you can just leave this out, or you can write 3 to the power 0. Similarly here, we don't have 5 on couple of them. So either you can leave that as it is, or just write 5 to the power 0 and 7 to the power 0, same logic carrying forward. So effectively, in this case, we are considering the lowest power of each prime, and that is what we are taking a note of in order to get the HCF. So this is a very simple idea, provided you have the factorized form. There are other ways to figure out LCM HCF as well. depending on cases. I'm not going that much deep for this problem. But anyhow, as I mentioned earlier, I mean, this is a very straightforward problem because n to the power 1 is 3 to the power 4. N to the, sorry, n1 is 3 to the power 4. N2 is 7 to the power 16. So I'm just writing this separately. I want to dedicate this level for three powers of 3, that is. And N3 is missing. So we don't know what N3 is. LCM of these three numbers is already given to us as this thing, right? 3 to the power 4 into 7 to the power 16. Now, what you need to understand is these two numbers are already fixed. I mean, you cannot change this. We are just looking for the possibilities of N3, right? Now, straight away, I hope you can identify that the power of 3 in the LCM is 4. So in turn, what it says is the maximum power of 3 of all the three numbers could be 4. So N1 and N2 we already know. I mean, N2 doesn't have a power of 3, so that is 3 to the power 0. So N3 can have anything from 3 to the power 0 to 3 to the power 4, right? So power of 3 in N3 could be anything from 0 to 4. Similarly, for powers of 7, N1 doesn't have a power of 7. So, and N2 has already 7 to the power 16 in it. LCM, you can find there is already 7 to the power 16. So, N3 can have anything from 7 to the power 0 to 7 to the power 16. Again, same idea. I mean, even if this has 7 to the power 0, or because this already has 7 to the power 16, I mean, LCM will automatically have 7 to the power 16. So, I mean, the easy part that I earlier mentioned, the easy part was because if you notice, I mean, this thing is as it is here, and this thing is as it is here, the powers, that is. So N3, you have the wide range of all powers of 3 from 0 to 4, and similarly all powers of 7 from 0 to 16. So you have this entire range open for you to take for N3, and any combination will be fine out here. By combination, I mean you can have N3 as 3 to the power 0 into 7 to the power 0. You can have 3 to the power 0 into 7 to the power 1. So any combination of these two things is feasible out here. So all you have to do is figure out how many combinations are there. Now, this very basic idea of counting here. So there are 5 possibilities out here, 3 to the power 0 to 3 to the power 4. Do not miss out counting 0, by the way. So there are 5 possibilities for powers of 3. And correspondingly, you have 17 possibilities for powers of 7, right? By correspondingly, I mean, for suppose you pick up 3 to the power 0. In that case, you can take any 17 powers of 7 from 0 to 16. You pick up 3 to the power 1 again for each of I mean for each power of 3, that is, you can take 17 powers of 7. So for each of them you're getting 17 possibilities. So for 5 of them you should have a total of 5 into 17, that is 85 different possibilities for N3. It was a very straightforward question. Those who have got it, I mean, I believe it should hardly take 10 seconds to solve this problem. I mean, just because this 3 to the power 4 and 7 to the power 16 is as it is. Just because this is an easy problem, let me show another variation out here. So suppose N1 was 3 to the power 4, N2 was 7 to the power 16, and let's say N3 is missing. We need to find the possibilities, and the LCM of these three numbers are 3 to the power 4 into 7 to the power 17, suppose something like this. Now, in this case, what you will find is powers of 3 here, we already have 3 to the power 4, and the LCM also has 3 to the power 4. So the same thing as in the problem, I mean, the question that we did just now. So N3 can have powers of 3 from 3 to the power 0 to 3 to the power 4. This thing, again, we have full flexibility. But here, you'll see that the LCM is 7 to the power 17. LCM is having 7 to the power 17. But N2 is 7 to the power 16, and N1 doesn't have a 7. And just by the basic idea that I discussed at the very beginning of the solution, the highest power of 7 will be picked up in LCM, right? And the highest power of 7 has to be 17. It cannot be in N1, cannot be in N2 because those two are already given. So N3 must have 7 to the power 17. So in this case, this is just a fixed possibility. 7 must have 17 powers in it. Otherwise, this thing can never happen. So LCM cannot have 17 powers of 7. So in this case, the only flexibility we have is in choosing the powers of 3. And that is 5 different ways we can do that. And in each of those cases, the powers of 7 has to be 17. So N3 will just have 5 possibilities in this case. So I just wanted to show one variation because this was a very straightforward question. But coming back to the problem, I hope everything was understood. The answer is 85, by the way. And yeah, that's all I had to add for this question. Thank you for joining in. All right. So we have been given cube root of 100 for some reason. Maybe it will be required in the problem later on. So cube root of 100 is 4.6415, whatever. How many natural numbers are there whose square has at least 5 digits and cube has at most 8 digits? Okay, great. So whenever you have a question like this, let's say the natural number is n. So let us break these two constraints and handle them individually. So there are two constraints out here. First of all, the square of this number, so square of this n, whose square that is. So square of this number n has at least 5 digits. So first of all, whenever the question is saying at least 5 digits, just simply think about the smallest 5-digit number that we have. The smallest 5-digit number that we have is 1 followed by 4 zeros, right? So this will be the smallest 5-digit number that you can have. My bad. 1 followed by 4 zeros. So 1 followed by 4 zeros is 10 to the power 4. Don't make a mistake of 10 to the power 5. So in this case, n square can be anything that is greater than or equal to 10 to the power 4 because it needs to have at least 5 digits. And this is the smallest 5-digit number that we can have, right? Now this one we can simplify straightforward. So let's do that before we go into the other constraint. So here, because n is a natural number, it's a positive number. So we can directly take a square root here. So that is on both the sides. So let's do that. So n should be greater than or equal to 10 square, which is 100, right? So this is one simplified constraint that we have for n, which is giving me a the lowest possible value of n. So that is 100. So it could be 100, 101, anything beyond 100 as well. Great. Let's look at the next part. So very similar one. The cube of n. So and the cube. So whose cube? That is of n has at most 8 digits. So n cube should be less than or equal to. So it's just the other way around. It's saying at most. So maximum of that is. So less than or equal to the highest 8-digit number. Similar idea. The highest 8-digit number is all nines, isn't it? That is 8 nines, of course, number of digits. Now, this is something I'll show here, and now I understand why the cube root of 100 is given anyhow. So in this thing, whenever you have to simplify something like this, just think about this. Think about this for a minute. How do you figure out the cube root of this number until unless you have a calculator and this has been, or the cube root of this 8 nines. This number has been already provided to you. I don't even know how to, tell this. What is this? 9 crore, 99 lakhs, 99,999, whatever. How do you directly take a cube root of this? It's not a very simple number to do, right? But it can be actually simplified to a certain extent as soon as you consider this to be just less than 10 to the power 8. Because think about this. What is the next number? So the next number is 1 followed by 8 zeros, isn't it? So it's just the next number, the smallest 9-digit number, something like that. So the point is, because the scope of thinking is limited to natural numbers only, we can do this very, very safely, no issues at all. So whenever you have a thinking related to number of digits in terms of natural numbers, you can always do this. It's a very smart way to handle this in terms of number of digit type of questions. I mean, whenever there's a limitation in terms of this number has to have this many, minimum this many digits, maximum this many digits. So always think in powers of 10. So the lower limit you'll always get as greater than equal to, so that will not be an issue. But for the higher limit, you'll always have less than something. I mean, it will not be, I mean, you cannot take this number, right? I mean, you cannot consider it to be 10 to the power 8. In this particular context, that will not be a problem, but in certain cases, you have to be careful about that. But anyhow, let's carry forward. So what we know is n cube has to be less than 10 to the power 8. Again, do the same thing, take a cube root on both the sides. So n should be less than. Now here, what I'm going to do is, see, I'm visualizing this as 10 to the power 6 into 10 square. Okay, so I'm going to take a cube root on both the parts individually. So cube root of this, so that is 10 square, which will be 100. And cube root of this is basically this 4.6415, which has been provided right in the question. Cube root of 100 has been given. This is 100, by the way. So this into 4.6415. Now, please understand, I mean, don't try to approximate this immediately. You will make a mistake if you don't do this properly. So just leave it as it is. And this is very easy to do, right? I mean, just shifting of decimal. So you'll have something like this. So n is less than 464.15. So you have these couple of constraints. One was earlier figured out. Now you have this. Let me take both of these. So what you have is n should be greater than equal to 100. That is the first constraint, and less than 464.15. So if you think about it, all the natural numbers from 100 to 464, I mean, you can actually consider 464 because that is still less than 464.15. So you can take up 464. So this is what I was talking about earlier. If you approximate too much, you might miss that out. So don't approximate beforehand. Let it be. I mean, it won't be too much of an issue. Just go ahead and calculate with the given value. It has been given for certain reasons. So anyhow, so you have this range, so 100 to 464. Again, there is another mistake that you can make. Don't take a difference of these two. In this range, the number of natural numbers will be 464 minus 100 plus 1, because when you do or when you take the difference of the two numbers, you're actually counting the gaps or the intervals between the numbers. You are not considering the total number of terms. The total number of terms will always be one more than that. So you can take an example, 10 to 20, you can just count it in your fingers. There will be 11 numbers, not 10 numbers. So out here, you'll have a total of 365 numbers. I mean, 365 is not a given value in the option. So option D, none of these will be the correct answer here. So few things I wanted to add to this. There's not too much to explain out here. Um, I mean, sometimes, I mean, this cube root of 100 thing, I mean, this might not be mentioned. You have calculators for that, but in that case, I mean, you can directly take a cube root of this if you're using calculator any which way. I can give you a scenario in which calculator is not at all allowed. So for example, if this question would have said cube has at most 9 digits. So in that case, this idea that I explained also comes in handy. So if cube has, let's say at most 9 digits, so this will be the constraint, right? So you'll have 9 nines or something. Um, and that will be just less than 10 to the power 9. So I hope you can see that 10 to the power 9 is actually a perfect cube. So if you take a cube root on both the sides, so you'll have something like n less than 10 cube. So now this will be easy enough to count, right? So this idea comes in handy in a lot of cases. I mean, I can give you a lot of different examples. But I hope that once you understand this idea, whenever you have a question related to this, I mean, a certain number has, or let's say a 5-digit number is multiplied to a 6-digit number. So what is the result? I mean, how many digits will the result have? If you think about the lowest possibility and highest possibility, you'll easily figure out there will be only 11. I mean, there will be two possibilities. Either the result will have 10 digits or 11 digits in it. So it's a smart way to actually handle this. But anyhow, I hope everything was understood out here. That's all I had to add for this question. Thank you for joining in. All right. So in this question, we are looking for how many 6-digit numbers starting with 489 are divisible by 789. Okay, great. So there are two things to understand in this problem. One is what is the range of numbers that we are looking for. So it has to start with 489. So basically, it is starting with this number. So when it says starting with 489, a 6-digit number, so effectively what it means is, so you have a number which is something like this. I mean, it's a 6-digit number. Well, let's say these are some arbitrary digits, A, B, C. Don't think that this is multiplied. This is just a whole number. So 489 ABC. This is a 6-digit number where the last 3 digits have not been given. The starting place has to be 489 with the starting 3 digits. So effectively, we are looking for the range of 489 to 489999, something like this. And you can count this in a lot of different ways. You can take a difference plus one, there'll be 1,000 possibilities. You can use PNC 10 into 10 into 10. So whichever way you want, there are total of 1,000 numbers out here. That is not required, I guess, in this particular problem. But anyhow, just for explanation purpose. And by the way, what is the constraint? What's the main constraint? So how many 6-digit numbers in this range? How many numbers are divisible by 7, 8, 9? So this is what we are looking for, right? So any number that is divisible by 7, 8, and 9 is effectively divisible by the LCM of 7, 8, and 9. So this is the basic idea of LCM. If your number is divisible by A, B, C, D, whatever number of devices, then it should be divisible by the LCM of all of these devices. Now, please understand out here one thing. When you have to find the LCM of these numbers, you can do it in a lot of different ways. But what I'm finding is 7 and 8 are co-prime to each other. So there is no common prime factor. 8 and 9 are co-prime to each other, as well as 7 and 9 are co-prime to each other. So this is something you can easily figure out because I mean, 8 is a pure power of 2, 9 is a pure power of 3. So it should not be a difficult thing to observe. So 7, 8, 9 being co-prime to each other. When we say co-prime to each other, it's always in pairs. So because they are co-prime to each other, the LCM will simply be the product of 7, 8, and 9. So 7 into 8 into 9 will simply be the LCM out here. So in this case, there are a lot of different ways. Again, you can calculate this. Smartest way will be 8 cube minus 8, by the way, the middle number cubed minus the middle number. So 7 into 8 into 9 will be 8 cubed, that is 512 minus 8, which is 504. So effectively what we are looking for is how many numbers in this range is a multiple of this. So that is the question. So we need multiples of this in this range. Now, the target is to find the first multiple. If you can figure out the first multiple, it should not be tough to count because anyhow, there will be not more than 2 numbers. There are just 1,000 numbers out here. So that is why initially I figured this out. But later on, I saw that there are both of these options, 1 and 2. It can never be 0, by the way. If I take 504 consecutive numbers, there will always be one number out there, and it cannot be more than 2 because there are just 1,000 numbers, so you cannot have couple of gaps of 504. But anyhow, we need to figure this out because we have both the options 1 and 2. Now there are a lot of ways to do that. So one thing you can definitely do is just divide 489,000 by 504 and figure out the remainder. The target is to find remainder. So one is by long division. You can definitely do that. I'm going to show you a smarter way. This might be a little useful for those people who are not very uncomfortable with calculation. So I'm not asking you to be brilliant in calculation, but if you are decent enough with calculation, this should be easy enough to find. So first thing what I'm going to do is, so when you have 489,000, just visualize with me. It's a very fast process, but you need to understand it once. So what I'm going to do is I'm going to first write 504,000 because I definitely know that this is a multiple of 504. Very easy to find, right? Nothing to think about at all. Now, if you think about 489,000, it is 15,000 less than this 504,000, right? Again, not a tough thing to do. All I'm doing is focusing on this 504 and this 489. So 504 minus 15 is 489. So obviously the 3 zeros you can put on both of this as well as this really doesn't make any difference. Now, the faster you can do this part, trust me on it. I mean, you can practice this in certain numbers. You can actually do the next step without writing this. And the next step is very, very smart actually. So what you do is just leave this thing as it is. This part, what I'm going to do is, again, I'm going to utilize a multiple of 504. Now this time around, because 504 is a 3-digit number, and I'm seeing that 5 into 3 gives me a 15, right? So I'm going to multiply a 3 to it. I know that will be a 4-digit number, so I'm just going to write that number first. So 504 into 3 is 1512. I hope that was not tough for you to find. But because this is a 5-digit number, so I'll just place a 0 here, just to make this parity. Now, I hope you can see that if I add a 120 to this, because this is in minus sign and this is also in minus sign. So if I add a 120 to it, this entire thing is equal to this thing, right? So effectively what I've done is 489000 is equal to this entire thing, right? Now, if you practice this, you will understand. I mean, it's hardly a couple of second thing. I mean, it won't even take 2 seconds to actually do this. This thing is no timer. All you need to think about this 15,000, which you can arrive very quickly. But once you are down to 15,000, then 1512 should not be tough to find. So it needs a bit of practice. So I suggest that you do that. It will be very, very fast compared to the long division. I mean, you can try it yourself. Both the process, you'll realize this. But anyhow, so what we have figured out is, so check this out. I mean, this part is a multiple of 504. This is a multiple of 504. So this should be the remainder, right? So effectively what we have found is, without using the long division approach, when 489000 is divided by 504, the remainder should be 120, right? Now, once you have figured this out, the rest is very easy, because if you understand the very basic idea of remainder, 489000 being a multiple of, I mean, sorry, leaving a remainder of 120 when divided by 504, what it implies is, if I subtract a 120 to this becomes a multiple of 504, right? So this thing is the basic idea of remainders any which way, right? If I subtract the remainder, it becomes a multiple of the divisor. Anyhow, but please understand that this number is not in the range. It is not in this range. We are subtracting 120 from it. But if I add a 504 to this number, it will obviously remain a multiple of 504, but it will also fall in this range, right? So you can check this out yourself. So all I will do is I'll just calculate this part. So 504 minus 120 is 384. And because there are three zeros out here, so I can just fit the 384 therein. So 489384, this will definitely be a multiple of 504. And once I figure this out, I just need to add 504 and check whether it also lies in this range or not. In this case, it does. I hope you can see that. So if I add 504 to this, it comes out to be 888 in these three positions. 489 remains as it is. And this is also a multiple of 504, right? But now, as I explained earlier, so you can see that 3 is never a possibility, because if I add 504 again, I mean, this plus 504 plus 504 is exceeding 1,000, right? And there are just 1,000 numbers here. So it is never possible that there will be three numbers which will satisfy this constraint in this range. So anyhow, these are the two numbers. So we are just looking for how many. So there are two numbers out here. That should be the answer to this problem. So it's a very simple problem, but I wanted to discuss the basic ideas again, because these things are very logical in nature. So don't try to mark them up. The calculation standpoint, the logical standpoint, the LCM idea, those things, you should not mug it up. Even when I earlier said, I mean, 7 into 8 into 9, you can calculate this as 8 cube minus 8. Just because I said this or somebody else told you, you should not muck it up. You should ask that question. If the mentor is not at that point right in front of you, you can at least ask yourself. I mean, where does this come from? I mean, why do I trust you? I mean, who are you to tell me that this thing stands, right? It's a very simple idea. I mean, 7 is 8 minus 1, 9 is 8 plus 1, and 8, just leave it as it is. So a minus b into a plus b is a square minus b square, right? So this part translates to 8 square minus 1, and then you multiply an 8 to it. Obviously, that results in this, right? So just don't mug things up. That's my point. Anyhow, I hope this idea was useful. A few things here and there were useful because the question alone is very easy, but there are few things, a few fine things which you can take away, I hope, from this question, at least from this calculation standpoint. There's a very easier ways to figure out remainders in certain things which on the face of it looks very difficult, but actually is not. Anyhow, that's all I had to add to this question. Hopefully everything was understood, and hopefully you apply these ideas in certain questions as well. Thank you for joining in. All right, we have an indices problem. So this expression is given, and the constraint is that this is an integer. Now, whenever I'm looking at this problem, the first thing that strikes me is in order for this entire thing to be an integral, resulting in an integral value, uh, each prime number, if I consider each of the prime numbers separately, for example, we have a certain power of 9. I mean, I don't care about the power, but this 9 is a 3 square, right? So I can definitely represent this as a power of 3. The 15 that I have, I can take it as a power of 3 and power of 5. Similarly, the power of 2 is power of 2, right? So that's a prime number in itself. Similarly, the denominator that we have, 30. So 30 is basically 2 into 3 into 5, right? So again, I can always represent this, right? So first thing I'm observing is that each of the literals out here, I mean the individual uh, indices that are provided are limited to powers of 2, 3, and 5 only. That is the first observation. The second thing that I'm straight away understanding is, see, if I have a power of 2, which is any non-negative integer, for example, 5 or 0 as well. I mean, 2 to the power 0 is also an integer, right? It is 1. So any non-negative integer, if I have here, so let me indicate that by I, that will result in an integer in itself, right? So that will not be a problem. But if I have a negative integer, so if I have minus I or something, so 2 to the power minus 5 or something, in that case, I'm not going to get an integral result, right? So 1 by 2 to the power 5 is a fraction. So what the question is indirectly telling us is that after the simplification, so there could be a lot of cancellation, right? Because the numerator and denominator both have powers of 2 and powers of 3 and powers of 5. So after the cancellations happen, the whatever powers of 2, powers of 3, and powers of 5 we have remaining in the numerator, they should be non-negative integral. So effectively the powers of 2, 3, 5 in the numerator, so I'm just writing this in short, should be non-negative integer. So this is what the question is actually asking us to do. So instead of simplifying usually how we will do, I mean by cancellation and stuff, I'm just going to do this a little visually. So what I'm going to do is I'm going to treat the separate primes separately. So 2, 3, and 5. I'm going to calculate the powers in the numerator and the denominator, and effectively after the cancellation. So whatever is the power in the numerator and whatever is the power in the denominator, after the cancellation, something will be left off, right, in the numerator. So this is how I'm going to approach this question. It might be a little easy to handle this. So just notice separately. So for the numerator part, powers of 2 first. So the only thing that contributes any power of 2 is this 2, right? So, neither 9 or 15 has any powers of 2. So we'll simply have a 13 minus a from this. Now, as I explained earlier, 30 is basically 2 into 3 into 5. So any power of 30 will be equally distributed among 2, 3, and 5, right? So if I have 5 powers of 30, that will be 5 powers of 2, 5 powers of 3, and 5 powers of 5, right? So whatever are the powers of 30, that will be equally distributed among 2, 3, 5. And we already know the powers of 30 is this 10 minus a plus b. So effectively what I can do is not only for 2, for each of these, I can straight away write this, right? You'll have that many powers of 2, that many powers of 3, and that many powers of 5. So this is pretty straightforward done. So let me complete this for 2. So after the effective cancellation, this minus this will be the remaining powers of 2, right? Numerator's power minus denominator power. So what we have is 13 and 10. That's a difference of 3. Minus a and minus a cancels out. And then we don't have a b in the numerator, but denominator has a plus b. So when we subtract, we'll have a minus b, right? So I hope you can see how I'm doing this. So constant separately, a separately, b separately, always fast to do. Let's do the rest of this quickly. First, I'll focus on 5 because 3 in the numerator is from both of these, right? So I'll come back to the 3 later on. Let me handle the 5 first. So 15 is going to give us 5, and as many powers of 15, that many powers of 5. Same idea as 30. So we'll have 11 plus b out here. Again, let me do that. So 11 minus 10 constant separately. We don't have a plus a any a out here, but this is minus a, right? So minus of a minus or minus of a, that will be plus of a, and the plus b cancels off. So this is the effective power of 5. What about 3 now? So 3, check this out. I mean, this is 9 to the power 25 minus a. So if I have 9 to the power 3, or let me take 9 to the power 7. So that will be 3 to the power 14, isn't it? Whatever are the powers of 9, there'll be, couple of threes from each 9, something like that, right? So 25 minus a we have. So that will be 50 minus 2a, number of threes from 9. But the 15 also has some threes in it, and that will be as many 15s, right? Because 15 is just 3 into 5. So if I have 7 powers of 15, I'll have 7 powers of 3 and 7 powers of 5. So 15 will have that many powers only. So just another 11 and another b, right? All of this is in the numerator. So now let me do the same thing. So constant separately first. So 50, 11 minus 10. So that is 51. Minus 2a and plus of a. By the way, we are taking a difference. So minus 2a plus of a. So that will be minus a. And the plus b cancels off. So nothing left off. So these are the effective powers remaining of 2, 3, and 5, right? Now let me get into the question, what we are actually trying to find. So we are trying to find the maximum value of a plus b. Now, if I have to find the maximum of a plus b, so if I'm trying to maximize this, notice the plus sign out here. By the way, don't read it as plus minus. So notice the plus sign out here. So in order to maximize the entire thing, I need to maximize a and b individually as well, right? I mean, this should be this should be a common sense thing. I mean, if I have two variables which are added, if I maximize both of them, then the sum will automatically maximize, right? On the other hand, if I had tried to maximize a minus b, the objective would have been to maximize a and minimize b. Then the difference would have maximized, isn't it? But in this case, we just have a sum, so we'll try to maximize both a and b individually. Now, check this out. I mean, this 51 minus a is actually going to give me a maximum. The 1 plus a is not, because if you remember initially, this is the constraint that we had, right? So powers of 2, 3, 5, the effective power. So let me write this as, instead of powers, let me write effective powers, because that is the same terminology I've used here. So the effective powers of 2, 3, 5 in the numerator should be non-negative integer, isn't it? So this a plus 1 being non-negative integer is not helping me at all, because now if you think about it, I mean, a could be 0, 1, 2, 3, all of these. I mean, even minus 1, for example. All of these cases, a is actually coming out to be a non-negative, a plus 1 rather, is coming out to be a non-negative integer, right? So in this case, we are actually getting a lower limit. So if you think it in terms of inequality, those who are comfortable with inequality, this will not be a problem, because non-negative integer, what does it imply? Forget about the integer part. So there are a couple of things here. So it has to be integer as well as non-negative. So forget about the integer thing, focus on the non-negative. Non-negative implies greater than equal to 0, right? So you can understand this very, very simply. This a plus 1 greater than equal to 0 implies a has to be greater than equal to minus 1. So this is not a max. This is not giving me a maximum value of a. This is giving me a minimum value of a, isn't it? But from the other one that we have about a, that is 51 minus a, this is actually going to give me an upper limit. Just notice this, if you want to do this with inequality, 51 minus a greater than equal to 0 implies 51 is greater than equal to a, or a is less than equal to 51. So the maximum value that a can take is 51, right? Just using common sense as well, you can do this. I mean, if 51 minus a has to be non-negative integer, I cannot take a more than 51 any which way, right? 8 being 51, 50, 49, 48, all of these are acceptable, but I cannot take 52, for example. If I put 52 here, this becomes negative. So I'm naturally getting a maximum value, right? So this tells me the maximum value of A is 51. And similarly, this one will tell me that the maximum value of B is 3, right? Same idea. So this is what our objective was. So maximum value of A is 51 and maximum value of B is 3. In turn, the maximum value of A plus B should be 51 plus 3, which is 54. I think we have options for this as well. Yeah, option B should be the answer out here. So just a simplification approach that I explained out here. If you understand this idea specific to this problem, you will automatically find shortcuts. I don't need to tell you shortcuts. So that is just the observation part. That you will automatically identify. But please understand the simplification thing that I did. Couple of things to take a note of. Number one, I was just focusing on the powers because that is the main thing in this context. Second thing, when I was doing those cancellation of the powers, or rather the numerator and denominator thing, notice that I was taking the differences in terms of the constant separately, the variables separately, and also the specific variables separately. I took the differences of A separately and B separately. This always helps, and this is not specifically for this problem I'm talking about. There are a lot of Venn diagram questions as well that I've seen in actual CAT papers and all, in which, I mean, if you treat these kind of things in this way, you calculate with the variables separately and the constant separately, it saves a lot of time. I've actually experienced this firsthand. So just try to simplify your calculation as much as possible. Just focus separately and it automatically becomes simple. You save a lot of time as well as your accuracy improves. So I hope there are few things that you can take away from this problem apart from the solution in itself. And that's all I had to add for this question. I hope everything was understood. Thank you for joining in.
Hopefully you liked the solutions we provided for these questions. And if you did like it, do not forget to like the video and share, subscribe, and comment. Do subscribe to the channel and click on the bell icon. In that case, you'll get notification as soon as we upload a new video. And if you want to check a bouquet of courses that we provide, so we have a huge variant of courses from customizability to full preparation. You can check our website www.mathoratory.com. I'll leave the link in the description below. And have an enjoyable preparation ahead. Welcome to the Mathoratory family and have a good exam ahead.